Okay, here we are once again. The physics video lecture, Physics 107B video lecture 15. So this is the day before the exam, and this will be actually quite short, but I first will talk about the coaxial transmission cable, transmission line that we left, that we didn't complete last time. And that'll segue right into a couple home exam problems that I'll kind of give you a heads up for. Good, so starting with the coaxial transmission line. And we're looking for modes that don't exist just in a circular tube. The reason being that, let's go ahead and set this up here. So we've got our coaxial line here. Here's our z-axis. Radius A inside, B outside. Perfect conductors as before. We're going to be able to support an electric field in here, even with a constant potential, because we can keep the potential differences. We can maintain a potential difference between the inner and outer radius. Okay, so let's go ahead and set up Maxwell's equations again. Okay, well, already used up that board. So we had last time at the board from the two curl equations, we had d ey dx minus d ex dy equal to I omega b sub z, and d ez dy minus d ey dz was equal to I omega b sub x. Actually, let me write the field. This is what we were working with last time, we're still working with. So we have E equals E0 of x and y e to the I k z minus omega t, and then we have the same thing for the B field. That's what we're starting off with. K z minus omega t. So yeah, the two curl equations gave us this. The z components of, we're talking about the transverse modes, right? The z components of B and E vanish. Z, Y, Y, Z, X. So, EZ 0, E sub Z is equal to 0. So we have E sub Y, and that's right off of this right here. Okay, this vanishes. So we can already put in the IK E sub Y. Now that we have these up here, okay, of the Z derivative. Good. Good. So omega over k b sub x, of course we recognize the ratio of E and B as just being C, so that tells us that C is just omega over k, so that's good. If we take, in addition to this, the divergence equations, divergence of P equals 0 and divergence of B is equal to 0, we will have dEx dx plus dEy dy equals 0 now. We don't have the z component. dx dx plus d dy dy is equal to 0. And of course we have those curl components as well. So let's go ahead and write those down. Not in this form, but just from the operator itself. And the same thing for B. Or dB. This should have been yx, xy. Okay, so what we have here is just a set of two-dimensional equations that we've actually solved before. And what we do is we transform these two-dimensional equations to cylindrical coordinates, okay? Because the differential equation just involves the cross-section, transform to cylindrical coordinates, solve them, and then multiply the e to the I kz minus omega t back on, and that gives us our solution. So these are the 2D equations from electrostatics. And magnetostatics. So we can write their solutions. And I'll just use this side of the board. So what do we have here? In fact, I can write the whole thing. I don't have to write them separately. Yeah, let's just go ahead and write the solution and have a good look at them. So we're looking at E, S, Phi, Z, and T. Okay. Cos Kz minus omega T. So once we write these down, we'll discuss them a bit. S hat and V, S, V, Z, and T. Okay, we're in cylindrical coordinates. We're going to have A times the cosine Kz minus omega T, speed of light times S. Okay. And this is phi hat. So let's go ahead and ponder these. I can segue right into what our exam question is going to be. So these are the solutions traveling in Z direction, and this is the radial S. So if we were to just continue using this picture here, yeah, we could have X, Y, and Z like this, then yeah, our S hat vector is just directed away from the Z axis. Okay, so it's always say if it's on the surface, it's right here, but that's a good way to draw it. Okay. There's our S hat. And our phi hat is going to be, tangent. Okay, phi hat. Yeah, so that's important. We're in the cylindrical coordinates, and so notice the E field is directed radially outward. The B field, it's your right-hand rule type of B field, right? They both get weaker linearly in S. The fields only exist in between, okay, in between these inner and outer radii. And an important note is the boundary conditions. They're just automatically fulfilled. E parallel is clearly equal to 0. You could say almost by construction, right? The parallel component is going to be the phi hat and the z hat, which doesn't exist here. And then the perpendicular B field is also equal to 0 because the B field is proportional to the phi hat. So it's those, the circular B fields. So there the boundary conditions are fulfilled. Let me put a note here that goes above these. Solve in cylindrical coordinates. So you're going to want to have the cylindrical coordinates handy too, because I'm going to move right on to what our exam questions are going to be discussing. So one of them, I'll just start over here. We're taking an infinite cylindrical current. So we can think of it as a particle beam. So exam. So let's go ahead and make the particle beam in the z direction like this. So we've got x, y, z. We've got an infinite beam of particles out to radius a. Okay. Infinite, but of course that's just for us a cylindrical charge and current distribution. Okay. So infinite particle beam. So because of that, we can say that it has charge density rho, so that's charge per volume. We'll just say it has a total current I, and do we need anything else? That'll do the trick. Okay, that'll be enough. So that'll characterize this, and because we have a charge density and a current, if we needed, we could get a velocity, right? We can get we can get a current density as well. So we can get a current density. And then I'll ask you to do something about this, okay? I'll ask you to do something about it, and it was just a good reminder that we'll be using cylindrical coordinates as a natural coordinate system to use here. So that's a good one. You're going to enjoy this one. And in addition to that, I have one involving the Maxwell equations in vacuum. Yeah. So that's one. Maxwell equations, which we've done enough with. and then some more just wave equation type of problems. So thematically, this is really going to be good for the chapters that we've done. And we're going to be starting a new chapter, so I'll just leave it at this. This is what you can prepare for. You know, get yourself set up with this object here, your Maxwell equations. You know those wave equations, and I think you'll enjoy it. So I'm going to leave it at that, and then we'll pick up after the exam with the next chapter. Good. See you then.